All right, so welcome to the SDR Forum. We've got two speakers today. Scotty's going to talk, and I'm going to talk. Scotty, WA2DFI, was first licensed in 1967 and has been continuously active since that time. He is active on Mobile HFCW on APRS. He's an advisor for Explorer Post 599, a BSA-affiliated ham club for teens in the Phoenix area. He's also been involved in the Open SdrForumTangerine project for the last 12 years. He's the TAPR director and currently serves as the TAPR vice president. That's the Tucson Area Packet Radio Association. Scotty's also active in the production of Open SdR components and other SDR projects, and is co-founder of iQuad Labs LLC, a supplier of Open SdR systems and other software-defined radio components. He currently works at SdrForumTangerine, a computer consulting company that specializes in FPGA
feedback too much, right?
and SDR design.
So I want to talk about a new TAPR project called TangerineSDR, and I'll tell you why we came up with that name, or at least my excuse for coming up with the name, in a minute. So I got questions first. So Raspberry Pi computers, everybody knows what that is, right? Okay, I want to know, how many do you own? 5? 10? 30? Did he say 30? Okay, 30. Do I have one? Anybody have more than 30? Okay, that's good, but now you have to subtract the ones that are still in the box. They don't count. What? No. Raspberry Pi single board computer. So how many are still in the box? You still have 30? So 25. Anybody else have 25? Okay, you're the winner. I don't know what you win, but you win. Okay, so how many people know what HamSci is? Okay, pretty good. How about OpenHPSDR? Oh, okay, even more. How about OpenResearch.Institute? See, I know you guys that have your hands down weren't at the TAPR forum this morning because we talked about this. Okay, so a couple. How about TAPR? Okay, good. Well, those are all different organizations. That's what the point I was trying to make. So that, what does TAPR do? This is a TAPR project. So what does TAPR do? Well, we support R&D. So if you have a blazing idea that you think is going to change the face of ham radio, come to us and talk to us, and maybe we will help you fund PC boards or prototypes or something that you need money for. Because we figure if you're going to put in all your sweat equity and all your brain power, we don't want you to have to buy the stuff too. So we would help you with your prototypes. And early volume production, this is exactly what we did for HPSDR, is we started out as the storefront for HPSDR because, that's cute, because the volunteers in the HPSDR organization didn't have the capability to do a storefront, and besides, you know how much, when you have a $150 board and you produce 500 of them, you can do the math pretty quick, right? That's a lot for one guy's Visa card. So they weren't willing to do that. So TAPR came forward, and actually we have you guys to thank because TAPR didn't have that kind of money either. So we depended upon the faith of the users to give us their credit cards 90 days in advance so that we could build the boards. So anyway, HPSDR was an organization, was just a group of experimenters. HamSci is a group of scientists. And Open Research Institute is a group of people that are promoting open source designs and software and hardware. And TAPR is a group that supports R&D, and we used to be Packet when we started out, but now we're kind of anything digital and radio. Oops, wrong way. So, what's our mission? Continuing our mission. This is what we're after, is a group of contributors who want to advance the radio art, and that's you guys. Not just us, but you guys. So these are all separate entities, but they complement each other. So together, the community is pretty strong with different areas of expertise. I keep going backwards with this thing. So how do we get the name? Well, you see, every good computer and radio has to have a fruit in its name. So, and I started out, if you were at DCC, I started out with orange sickle, because orange is really the best color. We all know that, right? But I didn't want to run into the trademark issues with the popsicle company, so I decided that wasn't a good idea. By the way, if you go to their website, they'll be happy to explain to you the proper usage of the term orange sickle. There's no trademark on it, but it is an orange creamsicle. And you have to say it that way, otherwise,
Test.
I don't know what happens to you, but that's what they say you have to do. So anyway, Tangerine is a nice, easy name. Orange is a new color, and of course you can get solder mask in orange. So stand back, red pitaya. Okay, so what is the project? So we're going to aim for a modular open source hardware and software platform for SDR, for software-defined radio. It's kind of like OpenHP SDR, the same, only different. We're going to draw the dotted lines in a different place around the modules. And it's a group of volunteers led by Tapper, dedicated to the building of the open source radio. So it's kind of like OpenHP SDR, and kind of like ORI, and kind of like HAMSI, but different. So now that you're all completely confused, so what is it going to be? Well, it's going to be a modular radio. So the idea is we don't want you to pay for a feature that you don't need. And if you have only a few $100s to spend, we don't want to exclude you. But if then you're rich, come see me afterwards. But before that, you can buy one for a bigger chunk of change, but it will do more. But some people don't need those features that cost all that money, so why should we exclude them from playing? It'll all be open source, modular, configurable, and expandable, and it will be really state-of-the-art. So that's the goals. Pretty lofty goals, but we're going to try. So it's all about trade-offs, and I'm going to go through these pretty quick because this is really, everybody knows if it costs more, you're going to sell fewer of them, right? I mean, if you go out in the flea market and you see a radio for $100, you don't have to think much to buy it, right? But if it's $1,000, then you probably have to think about it, right? No? Okay. I got some radios for sale over here in the flea market. Anyway, so capability and cost are linked, obviously. The more money you spend, the more capability you're going to get. But the interesting thing is, if you lower the cost, then you increase the user base, which lowers the cost even more because now we can build more of them. And the cost per unit goes down. So we get economy of scale by getting a larger, by smaller cost, we get a more economy of scale, which tends to drive the cost down. And it goes the other way too. So we make this super whiz-bang widget that only 5 people want to buy. It's too expensive because we only build 5 of them. So the way we get the larger base is you make it adaptable to different applications and expandable. So then I can target 3 or 4 or 5 different audiences for the board, and they're all going to buy it, so that means I can build more of them. So they'll be cheaper. So this is just how about a benchmark here? In 1985, TNC2 was $179. Well, in 2019 dollars, that's $420. Well, I don't know about you, but I'll buy something for $179, but I have to think about $420. Still, even today, even though that's supposed to be the same amount, I don't think so. So really, I think this is a top-end amount. I'd like to see the price less than that. So keep it as low as possible, and again, sell you only what you need to do your user task. And don't over-design. So some of our applications need a GPS disciplined oscillator. Most don't. So don't make that standard, because then everybody has to pay all the big bucks for that oscillator. So again, make the user base as large as possible by targeting different audiences. And get the word out to as many prospective customers as possible. Part of why I'm here, to encourage you to take a look at this project and see if you might be interested. And adaptability to different applications, I already said what I need to say about this. But you've got to make the hardware versatile enough, and this is a double-edged sword because the more versatile you make it, the harder it is. The more configurations you have, the more configurations you have to support. So you've got to be a little careful. I kind of tell users, all this expandability and upgradability is really not for you guys. It's for us to be able to give you 3 or 4 configurations that are across the spectrum quickly, so we don't have to relay out boards. We can plug things together and make a low-end one. We can plug different things together and make a high-end one. We can add a GPSDO and make an even higher-end one. And so you get to choose which one fits your needs and your budget. So the target cost is around $500. I think we're going to be able to make that, and that's for all the pieces. And the idea, too, is if we can make the pieces so that perhaps you can buy one piece and take it home and plug it on to things that you already have. Like, okay, let me ask you this. How many people have RTL SDR dongles? Oh, yeah, like at least half the people here. Well, you'll be able to plug that into one of our boards, and you'll be able to get on the air immediately. So let's talk architecture, but not this kind of architecture. So this is kind of it's a little bit different architecture. And you notice where I drew the dotted line here? So the Tangerine SDR includes the single board computer because there are things that this single board computer can do that in an FPGA or processor or whatever I put on the data engine board, it's too expensive for me to build one. They build 100,000 Raspberry Pis every month. They're $35. For $35, I mean, the single chip on this board would be $35 or more. So what I want to do is I want to utilize the most cost-effective method to get the features that I want in the single board computer and marry it up to the data engine, which does hard things like decimation and resampling and things like that that have to occur at high speed that need an FPGA to do the job. So that's the basic architecture. The target applications for it, I said ham-sized space weather station, Phase 4 satellite ground station, this Phase 4G, that's ORI is working on that. Academic users. So I was on the Red Pitaya website the other day, and they claim they've sold 30,000 units. Well, I don't think they've sold 30,000 to hams, so they're selling to schools and universities and teaching students about SDR. And then amateur communications like HPSDR type people, these last two categories here. You can build a whole radio if you want, so that kind of target audience. Remote ham radio, and maybe others we haven't even thought of yet, other applications. So some examples. So here is example of the personal space weather station. So you need a GPS disciplined oscillator because you have to have timestamps down to like 100 nanoseconds because this is going to be a network, worldwide network of internet connected radios. So when they collect data, in order to correlate it with other stations, you have to get a worldwide timestamp with 100 nanoseconds. Now think about that a second. Anywhere in the world, when the data is collected, you get a timestamp on the data that's within 100 nanoseconds of anyone else that's collecting the data. Try that about 10 years ago. Yeah, you couldn't do it. So anyway, so GPS-DO, 2 slots for RF modules. We're going to use one which is going to be a dual channel, so it'll be coherent, 2 channels of coherent ADC. And then they want a magnetometer on it. This is going to be like a low-speed interface, like we're going to measure the magnetic field of the Earth in 3 axes every 1 second. So it's very slow. So you can hook it on an I2C or SPI port, very slow port. But the real trick here is this part here is a gigabit Ethernet switch that we put on the data engine so that you can plug the other. It's a 3-port switch, so 2 ports are external. One goes to the FPGA, but now 1 port can go down to a single board computer, and the other board can go out to the internet. So now without any external switches or hubs or anything, now you've got a complete system here that has one connection to the internet. And the beauty of it is, since this is a switch, I can take this computer here can generate traffic to the internet, or we can take the data engine and generate traffic directly to the internet. So you're going to see why this is true, mainly because these cheap computers don't really have a lot of horsepower, not like compared to the FPGA on the data engine. So you don't want to put the single board computer right in the middle of your data path, because if you're doing 1 measurement per second, that works great. But if you're going to try to stream data, it doesn't work so good. So another application here, what we do is, in here you take an LNB. You can buy LNBs on eBay for $10. And they convert 10 gigahertz to 900 megahertz. You filter the 900 megahertz, and you undersample it, and now you've got a 10 gigahertz receiver. The uplink is a little bit harder. You have to really do the up conversion at the antenna with the PA at the feed point of the horn. But the point is that you're using the same board and the same interface and the same communications protocol for this as you did for this one. I did it the wrong way. This one and this one are the same board. It's almost the same hardware. You have to make this a little bit different. These two have to be different, but these are modules that plug in. So you get on the, say you buy yourself a personal space weather station and set it up, and then you decide you want to get on the satellite. Just go buy a couple extra boards and plug them in. Now you're on the satellite. You don't have to buy the whole setup all over again. So how about for an experimenter? You can buy a premium receiver, and of course now you're going to pay for a low phase noise oscillator and higher performance components, and maybe a faster single board computer. But if that's what you want, then you can configure it that way. And if you want a real low-cost approach, what we'll do is we're going to have an onboard oscillator on the data engine that's good enough. So if you want to use that good enough oscillator, you just don't even buy a clock module at all. And you can use the onboard oscillator. And you can get yourself low-cost ADC and DAC boards. I mean, if you say you want to be a loafer on 137 kilohertz, you know, the new band we have down the low frequency band, why do you need to sample 120 megahertz to copy, to receive that? So you can build yourself some low-cost boards, or will build them, and they'd be an option. And they'd be much, much cheaper than 120 megahertz boards. But if you want premium performance, then you put GPS-DO on there. Maybe we'll give you a new data engine that has many more logic elements, and it will run Linux right on the data engine. And then maybe you don't even need the client computer. It depends. This is kind of a pie-in-the-sky future thing, but this is something that's possible because the chips exist to do this. The problem is that chip there costs about $100 just for one chip. So it may not be a good solution when you can get a lot of that performance out of one of these $35 boards, so you just save 65 bucks. Okay, so after all that, what are we going to build? What's it going to be? So I took some liberties here with W.C. Fields. I actually thought that this was the quote that he had said, but this is what he actually said. So if you haven't been dazzled with this, I'll baffle you with the details now, because that's what I'm going to go into next. I've waved my arms around a lot and talked about modular this and high price this and high performance that and low cost this, but haven't really given you a lot of details yet. So we start with the same block diagram, and the piece I'm going to look at right now in the next slide is this FPGA and the 3-port switch. And again, this is a very simple block diagram, so a lot of stuff is left out. So the stuff that's left out now is things like this. So this is an Altera FPGA. This is the largest in the Max 10 series of FPGAs. It's 50,000 logic elements, which for those who haven't done FPGAs, that means nothing, but that's a reasonably good size. Max 10 is the low-cost version, so the highest Max 10 part is a good mid-grade, mid-level FPGA. And we're going to put some RAM on it, and mainly because we might want to use a soft core processor inside the FPGA, which is basically programming a corner of the FPGA to act like a CPU. Well, you have to have instructions for the CPU to execute. Well, you put them in the RAM. So you have to have that for the CPU to run. And the FPGA has an internal small amount of RAM, but this is much cheaper than the amount, and much bigger than the internal amount of RAM. And then this is serial flash memory, so this is for storing parameters and various other things. A micro SD card, battery backed up RTC. Now some of these things can be depopulated to make the board cheaper, because an entry level system doesn't need an SD card. It doesn't need a real-time clock. Those things are actually provided better on the single board computer, so you don't put them on this board. And power supply, so you don't have to have a 5 volt, a 3 volt, a 1.8 volt, and all these different supplies. You can use your station power supply. Gigabit Ethernet switch. I won't even discuss that for right now. Temperature sensors for if you want to determine, if you mount it on the top of your tower, you might want to know what temperature it is. If I live in Phoenix, I can tell you right now it won't work, but it's okay. Okay, so now the coolest part of this is the modularity. So the RF modules we're going to use 2 connectors for RF modules, and we're going to pick M.2 RF modules. How many people have solid-state drives in their laptops? Okay, with those little solid-state drives on those little boards, that connector is an M.2 connector. Only we're not going to use the same size board, and we're not going to use the same pinout. So whatever you don't plug your SSD into one of these connectors, okay? We're going to key it differently, so you won't be able to. But still, the point is that the connectors are very high speed, and they're 75 pins, which is enough to do a radio interface, and they cost 80 cents. And the mating connector is gold-plated fingers on the board, so it's free. It comes with the board. So we're going to use those. And the MEC connector is a historical connector that I happen to have a whole bunch of boards for, and it's a gold finger connector, so it's basically free. The idea being that when I get my prototype data engine boards back, I can plug an RF board right on it day one, and I can debug it. So this is really for debugging the data engine. How am I doing on time? Okay. So different RF modules, so there'll be one for the Space Weather Station. We don't need a transmitter. We're going to do, they call them signals of opportunity. That's like WWV, that's like broadcast stations, that's like existing transmitters that you listen to that you don't have any control over, but yet you can monitor them. So no transmitter needed, so we'll just use one slot and we'll have 2 synchronous channels, and that'll be one RF board. The other connector will not be used. For a phase 4 ground, you can do a receiver transmit module, or the way we mount the connectors on the board is collinear wise, so you can make a wide board and plug it into both connectors at the same time, and then you get twice the number of IOs in case you need to have a particular RF module that needs more IO pins than one connector can provide, than those 75 pins that I was talking about. And again, these are future modules that may, a 9361, this is like the analog devices version. These Lime ones, this 7002 I believe is on the Lime Mini, if you know what the Lime SDR Mini board is. But lots of opportunity to pick any kind of board that you want, or any kind of board that you tell us you want, and we build it for you, and there you go. So the first one we're going to make is for the Space Weather Station, which is also Space Weather Station. I'm going to talk about that tomorrow morning at the Ham-Sci Forum at 9:15 in room 4, and I'm going to address the specific needs of the Space Weather Station. But let me just say here that it's going to be an HF receiver, a 2-channel synchronous HF receiver, direct sampling receiver. And so these are the parts that we picked: 14-bit ADC at 122.88 megahertz, step attenuator, and we haven't determined what the low noise amplifier is going to be yet, but we'll have some kind of amplification there. And a fixed 60 megahertz low pass filter, because 60 megahertz is the Nyquist frequency, so we got a filter out above that. And then the idea is to have a optional plug-on filter on the board that you can put a jumper on and bypass, or say you live right next to one of them 50,000 watt AM stations, you could pull the jumper off and put a little trap on board that would null out that station, or a high-pass filter if you want to just get rid of the whole broadcast band. But it'll be optional, and ideally I see we'll make a little perf board, or make a board with series and parallel component pads, and then we'll let you pick whatever values you want to add onto that board to pick the roll-off frequencies that you want. And the other thing that we're going to do for the Space Weather Station is we're going to have, if I can do the right, we have a switchable calibration noise source, so the software can turn on a noise generator at a known calibration point and calibrate the whole hardware chain back to the A to T converter. And this is required because when you have 10,000 of these out in the field, you have to calibrate the measurements between them. So this is one of the ways that we do it. I mean, there's a lot of other things that need to be calibrated too, like the antenna and feed line, but this will at least calibrate the hardware receiver. Okay, so here's a kind of hard to see block diagram, but you can see the noise sources right here with switches, low pass filters for 60 megahertz, the optional filter that you could bypass with a jumper, the 31 dB step attenuator, followed by the LNA, followed by the ADC. And then this is digital data out here. This is your M.2 connector. And that could be on a board like, half the size of a cassette box, if anybody remembers what a cassette box is. Okay, now moving on to the clock module, we do basically the same thing with the clock module. And again, you can use one of these, which is reasonably good performance, and you could use that with no clock module. So it costs you nothing. It comes with the board. But if you want high performance or higher performance, we're actually planning for at least 2 different clock modules. One more of a low jitter, high accuracy clock that is not GPS linked. And then a higher end one, which you might use this. I don't know if we're going to use this chip or not. This has some issues. We're evaluating different GPSs now to determine what's the best way to do a GPS DO. But it probably, after talking to a couple guys in our Time Nuts group that are on the Tapper board, it's probably going to end up being a separate GPS and oscillator. We'll build our own GPS DO. This LE8MF here, this is actually a GPS DO module that you can buy that has the oscillator and the GPS and the phase lock loop and everything all on it. But it has some issues because it's not really designed for RF use. It's designed for timing use. So it has some erratic output, shall we say. So in other words, their output averages out perfectly well, but it averages out by going up here and then down there and then up here and then down there. And these rapid changes in frequency we don't like. So there's an example of one of them. Again, the 75 pin connector over here. We have a jitter reducer and a 4-channel clock distribution amplifier down here, Silicon Labs part. And then this was based on the LEA M8F. This is a U-Blocks module. I don't think we're going to do it that way because we actually got the evaluation kit for that module and we don't think it's going to work for what we want. And this is an example of the mid-grade performance, which is non-GPS DO, but it's got really low phase noise. You can see it goes down to, this down here is minus 160 dBc per hertz, this line here. So you can see it goes down very low. So this is actually the same oscillator that we used on the Hermes board. All the Anon boards use this oscillator. HPSDR used it, so it's a good oscillator. And of course, when we bought it, it was like $60. Now you know how much it is? $15. So that's good. Now, this looks like a really bad eye chart, but this is an example of what we want to do because we want to have the modularity extends not only just to the RF boards in the clock, but we want to be able to add, well, I'm getting ahead of myself. First, I'm going to talk about the interfaces to the computer, gigabit Ethernet and USB 3. And this is an actual 5 gigabit per second USB 3 interface. So we're going to have a 5 gigabit interface up to 500 megabytes per second on that connector. Then we're going to have a USB 2 host. Remember I said you can use your RTL dongle? Well, that'll plug into the USB 2 host. And you'll be able to grab data off of VHF and UHF and either feed it to the Raspberry Pi or feed it to the FPGA, whatever you want to do with it. And then dual gigabit RJ45 ports for gigabit Ethernet. So aggregate of 100 megabytes per second. Because, and you say, well, isn't that 200 megabytes per second? Well, no, because it's a switch, so it's only one path. So I really only get 1 gigabit per second, which is about 100 megabytes per second. And they were planning a Wi-Fi option too, a Wi-Fi and Bluetooth option. I'm not sure exactly what you'll do with that since it's much lower speed than these other interfaces. But you maybe like to be able to control the radio with your phone. So you want a Bluetooth interface or a Wi-Fi interface. So now this is the other part that I haven't really touched on, but you want to be able to expand low-speed interfaces too, like sensors and things for the scientific group. Well, and there's tons of hats, shields, what do they call the other things? There's plug-in boards that go on Raspberry Pis and BeagleBones and things like that. So what we want to do is we want to be able to interface to those. So we're going to take a bunch of low-speed I/O off the board, and we're going to put it probably on a sub-shield because the thing is, I added up the BOM cost for this board, and the connector cost alone was $50. Ew, I don't want to do that. So what we may do is we may put a one huge connector on there, because this is all low-speed I/O, and then we'll sell a shield board that will have whatever connectors on it you want. So instead of putting all of them on there, we'll only put the ones that you want on there. So we'll include some high-speed I/O, not very much, but high-speed differential I/O, but mostly low-speed I/O and Raspberry Pi hat, Arduino Shield. People probably don't know about this. In Europe, this is a big standard. And PMODs are a big standard here, and Grove connectors are for analog and digital I/O. So the idea is we want to support all of these, so you can go out and buy one of thousands of different shield boards depending on what it is that you want to do. And again, these are the low-speed serial buses that are supported on the low-speed connector. And if we work it right, you can put shields on the top and the bottom and the sides. So the joke is it's a Raspberry Pi hat, right, which stands for hardware above. Anyway, I came up with hardware on top is what it stands for, HAT. Well, so we have hardware on top, hat, but we have it also below and to the side, so we have hat BS. Well, maybe that's not such a good term after all, but you ought to be able to plug these together. And if we do the pinout right, you could plug this board right onto a Raspberry Pi, right on the connector. And then you've got the I/O with no cables or anything. And this is, pardon me? Hardware attached on top. So we can have hardware attached on top, sides, top, bottom, or sides, so that's, never mind. It was not a very good joke anyway. Anyway, so I stole this off the internet. This is just an example of what you could do with a stack of boards. The idea is I don't really want the thing to grow out like this, so I need a giant case. I'd rather grow kind of vertically. And again, all of these different shields we intend to support. And future boards, bigger FPGAs, more RAM, more, bigger, faster, more money. That's about what the bottom line comes. But all the RF boards will still plug in, and you'll still be able to use the RF boards and the clock boards. Our web page, who would have guessed? I tried to get green tangerine, but it was taken already. You get that reference, right? Green tambourine, green, no, never mind. So, TangerineSDR.com. There is a web page there. It has a picture of a tangerine on it, so content's coming soon. As soon as I can twist somebody's arm, get a volunteer to help with the web page. If you want to help with web page, come see me. We need help. We all need big-time help. Email listserv. It's on a Tapper. If you're on any Tapper listserv, if you go to that control page, it's listed there now as one of the listservs. So there's the address. I'll leave that up long enough for you to burn into your brain. We're going to have a TeamSpeak chat probably on Monday evenings where it's just being set up now, and we've got this fine business address here. Notice our port number. He said I could have any port number, so that's the one that I picked. And that's all I have. So thank you very much.
Thanks, Scotty.
Are you wired up, or do you?
Hello. Give me just